Hey everybody, welcome to Video Notes 3.2. We're doing dot structures and shapes. Please read these sections of the book, chapter 12, and do the self-check problem. So find these pages and do that practice problem. You can check your answers in the back of the book. You remember how covalent bonding works? Two atoms share electrons. Oh, sharing covalence. So we can use electron dot diagrams to help us represent atoms and molecules and ions. So if it's an atom, find the atom on the periodic table. Use dots for its valence electrons. So look, I found nitrogen on the periodic table. I say it's in group 5A. I put 5 valence electrons around it as dots, and boom, I have the dot structure for nitrogen. Look at all these dot structures for atoms. So you can use the dot structure to decide how many bonds things will make, likely how many bonds. So count the single dots. Hydrogen will probably make one bond because it has one single dot. Fluorine will probably make one bond because it has one single dot. Nitrogen will probably make 3 bonds because it has 3 single dots. Now, that's just a guideline. It's a prediction. Atoms don't always act the way we predict. So we can do Lewis dot structures for molecules or ions. Find the atom that makes the most bonds and put it in the middle, or the least electronegative atom. Get a valence electron total. Start bonding. Give atoms octets or whatever they need. Don't go over the number of valence electrons. If you run out of valence electrons, multiple bond, and then check your answer. Look, it's CH4. We've got 5, 1, 1, 1, 1, 8 valence electrons. So put C, H, 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 H. Everybody's happy. 2, 8, 2, 2, 8, 8 total. 5, 1, 1, 1, 1. Plus 1 means minus 1. So we have to get 8 valence electrons totes. So N bonded to H's. 2, 4, 6, 8. Nitrogen's happy. Happy hydrogen put 2, 2, 2. Since it's an ion, we put the charge on the outside. Phosphorus, 5. Chlorine, 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 chlorine. Chlorine, so that's 5 times 7, 3, 5, 40. 40 valence electrons totes. E, Cl, 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 Cl. Wait a second. Phosphorus has 2, 4, 6, 8, 10 electrons around it. Why can that happen? So some elements can expand their octet if they're in this third row on the periodic table or lower, because third row means third energy level. Third energy level means you can have more than 8 electrons. So, and then we count 8, 8, 8, 8, 8 times 5 is 40. That's right. Chlorines are happy with 8. Phosphorus can be happy with 10. It's okay. Nitrogen 5. Chlorine, chlorine, chlorine. 21, 5, 26. 26 valence electrons totes. And in the middle, because it can make the most bonds, Cl's around it. And then give them 8, because 8's great. As a guideline. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I'm sorry, 26. Boom! All right, this is called a lone pair. These are bonding pairs. N2, we got 5, 5, 10 valence electrons. So N bonded to N, 2, 4, 6, 8, 10. Ruh-roh, ran out of valence electrons. What do I do? Run away? No, 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 Harbin, don't run away. Let's take these two and put them in between. So we have to erase those. So now 2, 4, that nitrogen's happy. Take those two and put them in between. 2, 4, 6, 8, happy. 2, 4, 6, 8, happy. Boom. So the dot structure for a nitrogen molecule is like that. Each atom's happy. We had to multiple bond because we can only use 10 valence electrons. So that's why multiple bond when you run out of valence electrons. Okay. Resonance, what does it mean? Well, let's write the dot structure for this. We need 5, we need 6, 6, 6. That's 18, and 5 is 23. But then this negative means plus 1. So 24 valence electrons to us. Put my N, add it to some O's. All right. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, so I used 24 electrons, but look, nitrogen's so sad. So, what can we do? Well, if you run out of electrons, you can multiple bonds. I'm going to erase those two and replace it there. Now, nitrogen's happy, all the oxygens are happy. But wait, why couldn't I have done this? I could. Why couldn't I have done this? Well, matter of fact is I could. So these are 3 dot structures that represent the same polyatomic ion, but it shows them a little differently, like double bond right, double bond left, double bond down. They're different, but they are all legitimate dot structures, and so they're called resonance structures of each other. Resonance structures of each other. Okay? We'll practice a few in class of each other. Not every molecule has resonance structures. These ions happen to be resonance structures. Okay, now that we can do dot structures, we're going to start looking at, well, what is a molecule's shape going to be? And that's going to depend on how the bonds go around it. So we start with dot structures. Boom, look at that. Okay. What you do is you find the atom in the middle and you count the areas of electrons around the atom in the middle. Carbon, 1, 2, 3, 4 areas of electrons. 4 areas of electrons. All right. What about here? 1, 2, 3, 4 areas of electrons. What about here? 1, 2, 3, 4 areas of electrons around the central atom. What does that mean? Well, there's this theory called VSEPR, or the Vesper theory, which stands for valence shell electron pair repulsion theory. All right, that's where the letters come from. What it says is that electrons are always in pairs. Electrons push each other away because they're negative, and this theory of electrons pushing each other away tells us the shape. So we said there's 4 areas of electrons on each of these, and those 4 areas need to spread out. So here's CH4 again. Those areas need to spread out. So if this is the carbon and these are the hydrogens, the farthest apart those 4 areas can get is 109.5 degrees in 3-dimensional space. This is only 90 degrees, so it's not going to be flat. It's going to be 3D. This shape is called the tetrahedral shape. All right. What about NH3? There's its dot structure. There's the 4 areas spreading out. It looks a lot like the tetrahedral. But wait, electron lone pairs, this lone pair, that's invisible. You can't see that, but it causes the rest of the atoms to bend a little bit. And so we get this shape, and this shape is called trigonal pyramidal. Okay? And then water, 1, 2, 3, 4 areas of electrons around the middle. Those 4 areas spread out, 1, 2, 3, 4. It makes what looks like a tetrahedral, but remember, these are invisible. So all we see is the angle. This is called a bent or angular shape. Okay, angular shape. So shapes come from the areas of electrons around the middle atom spreading out. All right, so these shapes are going to be linear. Dot structure. The farthest apart 1, 2 areas of electrons can get is 180 degrees. So this is called a linear molecule. That's its shape. What about this one? Oh, looks like the dot structure. The farthest apart they can get is right next to each other. This is also called linear. There's no central atom. They're just going to line up right next to each other. All right, are there more? You bet there's more. Look, there's BF3. Uh-oh, exception. Remember, boron is okay. Okay with 6, right? So there's 1, 2, 3 areas of electrons around the center. 3 areas can spread out to the corners of a triangle. Look, it's a flat triangle. It's not 3D, it's flat. So we call it trigonal planar shape. All right. What about HNO? That structure. 1, 2, 3 areas of electrons around the middle atom. Spread them out. 1, 2, here's what's up here. Well, you don't see it, but there's a lone pair. Lone pairs aren't visible, but they need their space. So this molecule will be angular or bent because that lone pair pushes those 2 atoms down. So there's our N, our O, and our H. And this is an angular or bent molecule. Okay, are there more? I betcha there are. So PF5, phosphorus is an exception. It's in the 3rd period on the periodic table. It has d electron. It doesn't have electrons, so it has orbitals available. So phosphorus can expand beyond 8 electrons because it has more orbitals to use. So what's the farthest 1, 2, 3, 4, 5 things can get? This is the farthest it can get. And so we have a trigonal bipyramidal. See the pyramid there? See the pyramid there? All right. So this is called a trigonal bipyramidal shape. What about SF6? Dot structure looks like that. There's 1, 2, 3, 4, 5 areas of electrons around the middle. So they have to spread out. This is what 5 areas look like. But if one of those, okay, so this is, yeah, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So in this one, this is a pair of electrons that's invisible. That's this lone pair. So it needs space. The most space, electrons need more space than bonds. The most space it can get is to push these atoms in the line and those atoms down. This is called a seesaw. Because look, oh look, I'm sitting here on a seesaw. And then, oh, I'm sitting here on a seesaw. Yay, I'm going to go down. Oh, I need head. And then you go up. And then we go down, up. Anyway, that's why it's called a seesaw shape. What about BRF3? Okay. Bromine trifluoride has 1, 2, 3, 4, 5 areas of electrons around the center. Spread them out. 1, 2, 3, 4, 5. The reason the lone pairs are in the triangle is because that's a bigger distance. But lone pairs are invisible. I can't see them. Can you see them? I can't see anything. And look at the shape of the atoms in the molecule. Make it T-shaped. All right. Are there more? You betcha. Okay. This is as complicated as it gets, folks. Sulfur can 1, 2, 3, 4, 5, 6 have 6 areas of electrons around it. It can expand its octet, so it doesn't have to stop at 8. The farthest 8 things can get is a square pyramid. All right, and down here you have a pyramid as well. All right, so it's called, so you have 2 of them. It's called the octahedral because it has 1, 2, 3, 4 faces up there, 1, 2, 3, 4 faces down there. There's an octahedral. This molecule is weird because xenon doesn't even make bonds, but humans made xenon make bonds. And xenon can have more than an octet because it has d orbitals, 1, 2, 3, available to use 4, 5, 6 things around the middle. That's it. 6 is the most things around the middle. This one, the 6 things around the middle are 1, 2, 3, 4, 5, 6. Wait, there's nothing there. Hey, there is something there. What is it? It's a lone pair of electrons, and so that's invisible. So the name of the shape is square pyramid or square pyramidal. All right, you saw the shapes. So what do you have to know? The shapes. How do you get the shapes? Start with the dot structure, and then count areas of electrons on middle atom. Spread them out, spread out, name shape. Name the shape. Okay, that's what you got to do. So you have to know the electron pair arrangement, then name the shape based on the atoms you see. Oh, hey, it's structural formulas. Look at how this shows how the atoms are connected. Okay, so structural formula tells you the arrangement. Molecular formula counts. Okay, molecular counts. So this is structural, boom, structural, boom. Molecular, we got to count the stuff. So there's 1, 2 C's, 1, 2, 3, 4 H's, and 1, 2 O's. What about this one? Molecular. All right, molecular, 1, 2 C's, 1, 2, 3, 4, 5, 6 H's. All right. I want you to practice matching the structural formula to the molecular formula. So these are molecular formulas. All right. These are structural formulas. So see if you can match them up. All right. Try to write molecular formulas for these. We'll check them in class. Hey, try these book problems. Know these objectives.